So let's look at the result of the integration. This was the program. It did a lot of scaling. So first of all, it looked at all of the images and found spots on them and used which of these stars and used them to integrate to index, which is to determine the 3 angles and 3 unit cell axes lengths, and then it applied that and integrated. So if we look at the indexing solution, the top one is primitive tetragonal TP with a 57 angstrom cell. The B axis is also 57 and 182 with 3 90-degree angles. So if you remember from the image that we looked at, it had a long axis of about 180 angstroms and a short axis of about 57. So this is consistent with the image. And then taking that indexing solution, which as well as the 6 unit cell parameters includes 3 angles of the orientation of the crystal, the spots are predicted on the images, and then a box is drawn around each spot and its intensity added up, and all of this, all the partial reflections on each image are added together. So if we look at this, it's an OK image for 900 images. It integrates several times and then scales several times until it has lots of times until it has a good scaling model. So we look at this. The likely space groups are P41 and P43, which are tetragonal with a 4-fold axis that is a screw, and these are enantiomeric space groups. One is the mirror image of the other. We can't tell which is correct until we solve the structure, or we're looking at real space. In reciprocal space, there's no easy way of telling. So if we look at the stats, the high resolution limit was 2.5 angstroms, which is pretty good. We are basically 100% complete. 5-fold multiplicity, so every spot is measured on average 5 times. I over sigma is on average 9. Our R merge is 12% overall, which is quite high, but not disastrous, and I don't know, a very, very high in the high resolution shell, but there is still some correlation. The CC half, which is 2 random halves of the data set, the correlation. So overall that's very high, and it's still greater than 0 in the high resolution shell. So we will take this data processing just as is and use it. If we look, this is what Xia 2 has given us. If we look at the data files, the one to use is PSP28A32 free. So if we just take a look at that. I made a mistake. Okay, so this MTZ file is our reciprocal space coordinate file. I'm just taking a look at the header of it here. So it has a dataset ID, crystal dataset name, so this is SAD because I specified sulfur as the anomalously scattering atom. Even though we're going to solve this by molecular replacement, I want to see the anomalous stats in the file later on. This is the unit cell. Slightly refined from before, so 57, 57, 182.75. That's the wavelength. This is the history of the file, so we see it's gone through Xia 2, it's had free R flags added to it, various scaling programs, and these are the columns, so you can consider this to be like a spreadsheet, where these are the columns and each row is a reciprocal space reflection. So we have HKL, which is our reciprocal space coordinate. We have I mean and sig I mean, which is the intensity and the error on the intensity. Sig F, which is F, and sig F, which is the F is the square root of the intensity, and Dano, which is the anomalous difference and the error on that, and then the I plus and I minus are the various positive and negative Friedel pairs, which we won't worry about right now. And we see this thing extends to 2.5 angstroms resolution, and this space group is P41, but we must remember that we don't know yet, and it may be P43. So if we just take a look, remind ourselves of how these space groups look. The correct place to look is the international tables for crystallography, but there's an online resource which is very similar, called the Space Group CD. So if we take a look at that, hypertext book of crystallographic space group diagrams, high resolution diagrams, number 76 is P41 and number 78 is P43. So if we look at P41, if we have an XYZ, there are 3 more symmetry related positions. If we look at this, it has a 4-fold screw axis and a 2-fold screw axis created by symmetry, and no other symmetry elements. There are no 2-fold axes here and no 4-fold axes. So that's P41. And if we look at P43, it's the same, but if you see the orientation of the screw axis goes the other way. We know that it's this from the absent axial reflections, so if we look at those, we get a reflection condition. Our L reflection, 0, L, must be a multiple of 4. So if we look at the log files, the pointless should show us this. Here we go. So these are the axial reflections C-axis. So this is for 0, L, and we look down the eyes. We haven't measured all of them, but for 9, 10, 11 there's basically nothing, and then we see a large intensity at 12, nothing again until 16, nothing again until 20, nothing again until 24. So this pattern, which I can see repeating and which I could plot if I were looking on the GUI, strongly implies a 4-fold screw axis, but we don't know if it's P41 or P43. So when we go into CCP4, I will create another version of the file that is re-indexed in the header to have the new space group. If we were going to solve this by experimental phasing, we also have unmerged files to put into software to find the anomalous scatterers. Okay, so next up would be to consider the molecular replacement model.